All right, back to actually solving the problem. We need a constraint. What is our constraint? And this is really the difficulty of a particular problem like this. All right, so I can't just claim the constraint is the surface area of the cylinder. There's much more going on here. The fact that the cylinder is circumscribed inside the cone is actually a more definitive constraint than the actual surface area of the cylinder itself. Right? It has something to do with being trapped in the cone. That's really the constraint. If you think about the geometric constraint, not the algebraic equation, but the geometric constraint on the cylinder is really the structure of the cone and the fact that this top of the cylinder is butted up against, in a sense, the apex of the cone. So it's not so obvious, but what we can do is use a similar triangle argument. Again, until you see a problem like this would really not be obvious unless you're really thoughtful, which most people aren't. Something like that. So I see there's one triangle for sure. Now, it's not just I have a triangle in this problem. This triangle exists throughout the entire symmetry of the cone. Right? No matter where I would turn this triangle, like if I rotate it around here, this triangular situation would exist no matter where I move this point along the circumference of the base of the cone. Right? So it's not just some arbitrary triangle sitting within here. This triangle is ubiquitous throughout the entire cone structure itself. It's a part of the symmetry of the cone. But we need another triangle, and we're going to introduce it right here, and that is this one. If I measure out from the center of the top of the cylinder, then I will be using the radius of the cylinder right there, right? And we know that that is RC. Now, I drew it down here in the beginning, but really it's more useful to see it here. So I'm going to write RC right there, right? Now, if we take this out of context a little bit, okay, let's highlight the two triangles. We have the larger triangle here, right, which has to do with the cone for the most part, right? It's defined by the height of the cone and the radius of the cone, and then this hypotenuse, which is really part of the surface area of the surrounding of the cone. And then we have this one here. Right? Once I introduce this piece, this radius of the cylinder, then this upper triangle here, which is of course similar to the outer one, right? That inner triangle there is really due more to the cylinder's position, right? It has to do with the cylinder radius, and it does have something to do with the cylinder height, right? Now I know that this height here is not the cylinder height, that this is, right, from this point downwards, but nevertheless, this triangle has something more to do, you might say, with the cylinder than the cone. So what I'm really doing right now is I'm relating cylinder quantities to the cone quantities in a proportional type of way because of these similar triangles. So let's take this triangle out of context for a moment and see if we can come up with a constraint. If I redraw the triangle, at least something that looks kind of like it, and it'd be perfect. Okay, that's quite sufficient for me. There. So we know that this is radius of cylinder. We know that this is radius of cone. Okay, so these two are proportional, and then we have that this whole height here is really the height of cone. We know that this height here is height of cylinder. All right, what we'd really like is something representing this here, that piece there. So let's just call it, I'm just going to call it L for a second, okay? L. So by usual proportionality of similar triangles, it must be that L is to RC, right? This length to this length. L to RC is the same as what? well, the larger triangle's left leg here, which is h, right, to the base, capital R. Okay, so that's true. No matter where you would turn this triangle inside here, right, the little one will follow, and this proportionality will exist throughout the entirety of this structure. So here is a relationship between the cone and the cylinder. Now L here, right, what is L? We know that L plus height of cylinder is height of cone. Now I can solve for L, because L I just introduced for the sake of the proportionality argument. Right? I really didn't want to talk about L per se, but I had to because of the way the proportionality was working out. So I should rewrite L in terms of the quantities we've been dealing with already, which is height of cone and then minus height of cylinder. Okay, so I should replace that here. I don't want to introduce any more new variables than I have to. That was just for the sake of argument. So h minus height of cylinder over radius of cylinder is equal to height of cone over radius of cone.